This is a video on simple harmonic motion. If a motion repeats itself forever, it's called periodic motion. There are many examples of this, many of which are quite complicated, but one that is much more simple is called simple harmonic motion. Some examples of this are a pendulum swinging back and forth, or, as we will see in this video, a mass on a spring. So let's consider a mass on a spring. So the mass is sitting on a frictionless surface, so the only force exerted on the mass is the spring force of the spring. The mass starts off a distance a to the right of the equilibrium position, which is indicated by a dashed line, and at t equals t naught, the hand releases the block. As you can see, the mass moves to the left, comes to a compressed position, and then moves back to the right. And we will discuss each one of those in turn. So at t naught, you release the block on the spring. The net force is to the left, so the block accelerates to the left. At t1, the block has moved far enough that the spring is at equilibrium. The net force is 0, but over the time interval between t0 and t1, the block has been accelerated to the left, which means that when the block reaches the equilibrium position at t1, it has some velocity v to the left. At t2, the spring is compressed again, so the net force is to the right. Between t1 and t2, the block has been moving to the left, compressing the spring. The spring has been exerting a force to the right on the block, slowing it down, so that's why at t2, the block is at rest again. At t3, the spring has accelerated the mass to the right now, so the velocity is to the right. Again, the net force is 0 because the spring is at its equilibrium position. This is exactly the same as t1, except the block is moving in the opposite direction. And finally, at t4, the block has moved back to its starting position, a distance a to the right of the equilibrium position. It's again at rest because over the interval from t3 to t4, the mass has been moving to the right, stretching the spring, which has been exerting a force leftward on the block to slow it down. Notice that at t4, everything about the system is identical to that at t naught. The block is in the same position, the block has the same velocity and the same acceleration. Thus we can define the period of this oscillation as capital T equals t4 minus t naught, where by period we mean the time in which it takes some periodic motion to complete one full cycle and come back to exactly where it was before. Another useful way to define this is to look at the inverse of period, which we call frequency, usually lowercase f. Where period is measured in seconds, frequency is measured in cycles per second, or hertz. So the period is looking at how many seconds does it take for the system to undergo one complete cycle, and the frequency is asking how many cycles pass per second. They're exactly the same, just inverses of each other. We can thus write the position as x of t equals a cosine of 2 pi time over the period plus phi. Let's break this apart for a second. So a is the amplitude of this oscillation. The block starts a distance a to the right of the equilibrium position at t naught. At t2, it's a distance a to the left of the equilibrium position, and at t4, it's a distance a to the right of the equilibrium position again. This motion can be described as a cosine. So we know that a cosine oscillates between +1 and -1. So if we multiply by a, that means that the position of this block oscillates between plus a and minus a, which exactly matches these pictures. Let's look at the first term inside the cosine. 2 pi times time divided by period. Well, we know that after one full period has gone by, i.e. going from t naught to t4, the system has to be exactly the same as it was before, which means the position has to be the same as it was before. For a cosine, however, that only happens after the argument has advanced by 2 pi radians. So when little t equals 1 period, then we need the cosine of 2 pi, which is exactly the same as cosine of 0. So that's why there has to be a 2 pi multiplying this factor. We also need to add in a phi, which is an arbitrary phase shift. The phi basically tells us where in the cycle we start. So for example, consider doing exactly the same experiment, but starting with the block to the left of the equilibrium position by distance a. So the spring is starting off compressed instead of stretched. If you let it go, it would go through exactly the same set of motions, but it would be shifted by half a cycle. It would essentially start at T2, then go to T3, then go to T4. At T5, it would be back at its equilibrium position, and at T6, it would be compressed again to the left. So it follows exactly the same pattern, but it's delayed in time a little bit. In that case, the phase shift phi would be equal to pi. So the phase shift we need to keep in there just to keep track of where in the cycle this system has started. We can simplify this a little bit by recalling the definition of angular frequency from the rotation unit. Remember, we defined omega as d theta divided by dt, the change in theta per unit time. Well, if you look at the first term in the cosine, after a amount of time capital T, then the angular change of the argument is 2 pi. So we can say that 2 pi divided by the period is exactly this angular frequency. So we can simply write the position now as a, the amplitude, times cosine of omega t plus phi. What about velocity and acceleration of the block? Well, we know that the velocity is the time derivative of the position, and we know that the acceleration is the time derivative of the velocity. So if we take one time derivative, the a is a constant, so it comes along for the ride. Derivative of cosine is minus sine, and because we're taking a time derivative, the chain rule pulls out a factor of omega to the front. So the velocity is minus a omega sine omega t plus phi. Exactly the same argument of the trigonometric function as before. So this means that the velocity, just like the position, will oscillate between a maximum value to 0 to a minimum value back to 0 and then back to a maximum value again. Taking another time derivative, well, we know that the derivative of sine is cosine, so the derivative of minus sine is minus cosine. Again, we're taking a time derivative. Chain rule pulls out another factor of omega, so in the acceleration, there is a factor of omega squared. Let's double check this really quickly, looking at the first two instances. At t0, the block is at a maximal position, so the position is maximal, and the acceleration is to the left, so it's maximal but negative. We know this is true because if the block is to the right of the equilibrium position, the spring will be pulling to the left on the block, so the acceleration will be to the left and it will be the largest. The block is at rest, so the velocity is 0 at that point, which makes sense. Sine of 0 is 0. If we look at the second instant now, t1, well, now the position is at the equilibrium, so the position is 0 with respect to the equilibrium, which makes sense because cosine of a quarter period later, if we plug in a quarter period, then we have 2 pi times 1 quarter, which turns into pi over 2. Cosine of pi over 2 is 0. So the position is 0 and the acceleration is 0, which makes sense because the spring is at its equilibrium position and it's not accelerating the block. However, the velocity is maximal and is pointing to the left, as we would expect, right? Sine of pi over 2, plugging in for omega t, is positive, but with this minus sign out in front, this means that the velocity is to the left, which is exactly what we would expect at t1. So these formulas completely describe how this system behaves. And in fact, these formulas, the fact that the position goes as cosine, velocity goes as minus sine, and acceleration goes as minus cosine, are the hallmarks of simple harmonic motion. Finally, a couple of general things to keep in mind. So first of all, the period, and therefore the angular frequency, only depend on the mass of the spring and the spring constant. What that means is that if we increase the amplitude of the motion, nothing else changes. So doubling the a out in front would not change anything else. So the position before was a cosine omega t. It will now be 2a cosine omega t, but omega will be the same as before. As long as there's no friction, this motion will repeat itself forever. And it repeats identically, so any given cycle looks exactly the same as the cycle before, or the cycle after, or the cycle 10,000 cycles later. They all are exactly the same. And finally, starting the mass at a different point in the cycle only changes phi. So nothing else will change. This won't change the magnitude of the amplitude. This won't change the angular frequency. It will only change the value of this phase constant.